All right, let me just redo this. Hi everyone, this is week 5 of Pal4Pal, mostly on vectors in 2 dimensions and trigonometry review. So this is the first set of review exercises on past like week 3 formulas. Or you could type and like private message us the correct answer if you find the correct answer. Remember to submit your answers if you find any answers. Probably should have gotten at least 2 already. Alright, I'll try to pull on random people. Alright. Okay. Okay, Darren, what's the answer to what's sine of 30 degrees? How do I do this? Okay. Wait, can you all hear me? Oh, there we go.
Oh, what the heck? I was in the bathroom, my bad.
Sorry.
Uh, what do you want me to do?
Uh, well, do you know that what's sine of 30 degrees?
The sine of 30 degrees is, where's my pencil? Okay. Uh, I think it is 0.5, 1 over
Yeah,
2.
yeah, that's correct. So this one be 1/2. Because if you draw like a triangle like this with 30 degrees over here. Maybe you remember from special right triangles. This is 1, this is 2, this is root 3, up to scaling, but that doesn't matter. So sine of 30 degrees, SOHCAHTOA is opposite over a hypotenuse, which is 1 over 2. All right, so this one's half. All right, pull in one more random person. All right, 7th person. Oh, that's Franklin. Okay, next person. Okay, Isaac. Do you know what's cosine of 315 degrees?
Uh, root 2 over 2.
Yeah, that's correct. Well, it's almost the same as the first question, except it's 315 degrees and it's cosine, which is adjacent over hypotenuse. Oh. Oops. All right, I think I should find random person. All right. Okay, one of the Jessicas. It doesn't matter which one. Do you know what's tangent of 112.5 degrees? If I do this.
-1 minus root 2.
Yeah, that's correct. For this one, you want to use the half angle formula. Well, one of the half angle formulas you need to be especially careful with. It's like the... Okay, I should start from the beginning. There's 3 formulas. One of them is plus minus, or 1 plus cosine theta. This is like the one you should be especially careful with, because you have a plus minus over here and you check the signs. But there's 2 formulas where you don't need to worry about the sign. And there's these ones and this one. And either one of these should work for this problem. Wait, this is plus, sorry. Yeah. And I should do the plugging in. So tangent of 112 degrees, 0.5 degrees, is tangent of half, new person, of 225 degrees. You just plug in the numbers. 1 minus cosine of 225 degrees is 1 minus negative root 2 over 2. This one's negative root 2 over 2 as well. This is, you multiply 2 on the denominator and on the numerator. This is 1 plus, oops. This is root 2 over root 2 plus 2, which is 1 plus, negative 1 minus root 2. All right, what's the last one? Okay, Felix, what's the answer to the last question? Cosine of this many degrees.
I got root 6 plus root 2 divided by 4, but I'm not sure if it's correct.
Yeah, this is correct. Very good. And the strategy for this is like you notice that cosine is periodic 360 degree wise. So this part is all like a multiple of 360 degrees. So like you don't need to worry about this at all. So all you need to do is to find cosine of 15 degrees. This you can use the double angle, the half angle formula, or you can use the other one, the angle subtraction. I'll just use angle subtraction here. Cosine of 15 degrees is cosine of 45 minus 30 degrees, which is cosine of subtraction is cosine cosine plus sine sine. Now you remember from the routine, like special angles. This is root 2 over 2. This is root 3 over 2. This is root 2 over 2 again. This is half. You simplify this a little bit. This is root 6 plus root 2 over 4. Or you can use the half angle, but for half angle to be a little bit more careful because you have a plus minus in the beginning. So you need to double check that 15 degrees is a first quadrant angle. All right. Any questions for this part? All right, good. All right. Let's look at the next part. All right, this is part about law of sines and cosines.
Hey everyone. I'll be walking you all through this problem, but I want to first see how much progress you can get by yourself. Let's spend some time to look at this problem for a while. If you have any like progress on like what lengths, you can just like message me. All right, I'm going to start explaining the first parts of this. I mean, some of the parts. And let's first look at triangle ABC over here. Does anyone know what we can use here to find length AC? Just like type in chat, say it, whatever. All right. So in this triangle ABC, we have two lengths, as well as the angle between them. So we can use law of cosines. And in this case, we will find that AC squared is equal to, um, and from here, wait, that's not correct. So we find AC is equal to 14. Like, does that make sense to everyone? Okay, I have to assume so. All right, so now let's take a look at AE. And in AE, we can do basically the same thing. It's just that we have a different angle and two different lengths this time. It's actually not necessary to. Wait, never mind. But instead, yeah, let's just look at AE for now because it's a good practice anyways. Find. And since we know cosine of 60 degrees is 1/2, that cancels with the 2 here. And we can just evaluate this. All right. I'll give everyone a bit more time to think right now.
You could use a calculator for this one.
All right, for this next part, let's look at triangle ADC since that's the one triangle we haven't actually looked at all. And over here, we can use law of sine since we're given an angle and the opposite side, right? So recall that law of sines states that the sine of angle ADC and after this, we can find angle, I mean the sine of angle ACD. And this is just basic computation since we can substitute all the values in. Like for example, angle ADC, sine of angle ADC was just root 3 over 2. And we know AC is 14 and AD is 16. And the rest is just computation. But after evaluating at sine angle ACD and taking the inverse sine, we find that the sine of angle ACD is either equal to 81.787 degrees or 98.213 degrees. And we know that the sum of angles in a triangle is always 180 degrees, right? So now we have two angles. We can find the last angle, which is angle ADC. I mean DAC, which is either equal to 21.787 degrees or 38.213 degrees. So now we just have one last step, and that's just to calculate the areas of each of these three triangles. And we have a formula for that. Remember that the area of a triangle is 1/2 of AB sine C, which just means multiplying the adjacent sides, multiplying by the sine of the angle between them, and dividing by 2. With angle ABC, this is and recall that the sine of 120 degrees is root 3 over 2. And this simplifies to 15 root 3. Um, Now we can look at triangle ADE, and this area is 1/2 times 12 times 16 times the sine of 60 degrees, which is root 3 over 2. So this area would be 48 root 3. And this last area, we we can just like plug it in, though this time it would actually require a calculator, and it would be 24 or 40 root 3. So now if we add up the possibilities, the two possible areas would be 72 plus 15, which is 87 root 3, I believe, or 103 root 3. So possibility one is, and these final answers are 87 and 103 root 3. Yeah, congratulations to everyone who got the answer correct. And next, I think Jonathan will be presenting.
So this is more review of trigonometry and complex numbers. So let's start with part A then. Um, so arcsine of 1 is just pi halves. So we can put arctan. Okay, so then we can copy arctan of 2 here. And we want to write our cosine of 3/5 as a tangent, as an arctangent, because we're going to put a tangent here. So if alpha is our cosine of 3/5, then alpha is like this in this triangle. So alpha is equal to the arctangent of 4/5. So now we just take the tangent of this using the tangent sum formula. So the tangent of arctangent of 2 plus the arctangent of 4/5 is equal to 2 plus 4/5 over 1 minus 2 times 4/5, which is equal to 14 over minus 3. Oh wait, no, this is 4/3, sorry. Just so 10 of this is 10 over -5, which equals to -2. So now we have just tan of pi over 2 plus this number whose tangent is -2. So we know that the tangent of pi over 2 plus x is equal to -1 over the tangent of x. So if we plug -2 into this, we find that the answer to this one is 1/2. Okay. Now we're going to do the second one then. Okay, so for this one, we're just going to multiply by the complex conjugate of 3 plus square root 2 oh, and then we can just expand out the numerator and denominator. So A is 6 plus root 6 over 11, and B is 3 root 3 minus 2 root 2 over 11. Yeah, so for this one, we just use complex conjugation. Um, for the third one, like, we write it like this. Yeah, so then we can just like put this into a calculator. So this is equal to 36.770 times e to the I 67.620 degrees. So in polar form, this is and we can write e to the I theta as CIS of theta, so this is just CIS of 67.620 degrees. Yeah. Okay, and for problem 4, so we can graph this onto the unit circle. So actually these are just the lengths of a 30, 60, 90 triangle. So that means that this angle is CIS of 30 degrees. So we take e to the I pi over 6 to the power of 2026. So we know that e to the I2 pi is equal to 1. So that means that when we multiply this 2026 times, it will cycle every time we multiply it 12 times. So 2026 divided by 12 leaves a remainder of of 10. So this is equal to e to the I pi over 6 to the 10, which is at CIS of minus 60 degrees, which if we put on the unit circle is 1 over 2 minus root 3 over 2 I.
Okay, so any questions about that part? All right, I hope you don't have any questions then. All right, now some new content. New content about vectors. So a vector is a quantity that has both magnitude and direction, often expressed as this like round bracket AB, which the A and B will explain later what it means. It's basically the component of the vector. It's like almost like a point, but it's like another quantity. Oh, or like that, yeah. All right, let's go over the basic definitions of a vector. A vector is sort of like an arrow. The vector from P to Q, like over here, this is P, this is Q. We call P the initial point and Q the terminal point, well, obviously. This vector is called PQ. Actually, PQ should be like this, with just one arrow instead of like a double arrow. So like Just keep that in mind. It should be one singular arrow. This is ray PQ. Just some conventions. Right. A vector is usually written in a bond face font, bold, like this, or with an arrow like U. Well, they're over here. So I can label this as vector U. The zero vector is the vector with nothing, so like I can't even draw it. It's sort of like that. It's like the zero vector, and basically it just doesn't move. And two vectors are equal if and only if their magnitudes and directions are equal. So like a vector is sort of like this arrow thing with a direction. And obviously if the arrows look the same, they should be called the same. And that's why mathematicians call two vectors equal, even if and only if their magnitudes and directions are equal.
All right, so adding vectors is actually really straightforward. In this case, all we do is we just add the first components together and the second components together. Like in this example, this 1, 3 corresponds to this vector here, since it goes horizontally right 1 and vertically up 3. And this 4, 1 corresponds to this lower 1. And the 5, 4 comes from adding them together. And yeah, we just add the horizontal ones together. 1 plus 4 is equal to 5. And the vertical ones together, 3 plus 1 is equal to 4. And there's actually quite a few graphical representations of this, but I think the most intuitive one is this parallelogram law. Basically, vectors are always the same, like no matter how you translate them. So we can move it. So if we look at this blue vector right here, we can move it right and up and place it right over here. And over here, now we have a vector, and if we look at the end of this one, it'll actually be the sums of them. You can try to prove this for yourself at home. I won't go through it since I think it's pretty simple, but this can be used to graphically represent vector addition. Yeah.
Um, oh, okay, so here we have a simple example of vector addition. So U has a horizontal component of 4 and a vertical component of 5. So U's terminal point is here, so we graph U like this. And similarly, V has horizontal component -5 and vertical component -2. So we graph V like this. No, for U plus V, we just add the corresponding component. So 4 plus -5 is -1, and -5 plus -2 is -7. So if we graph that on our coordinate plane, then the terminal point is here. And now we graph U from the end point of V. So we go 4 units horizontally and -5 units vertically. Which is basically the same definition as adding vectors. So this is why the endpoint of the shifted U is just U plus V.
All right, here's like the actual definition of the components. There are two unit vectors that have special names. I is called one, well, I is called I, and I equals to 1, 0, and J equals to 0, 1. In some textbooks, you see it written as I hat and J hat. Every vector can be written as AI plus BJ, and this is intuitive because if you have a coordinate plane, I is basically the vector that's one unit on the positive x-axis, and J is like the one unit on the positive y-axis. So we have any point, say like 1, actually like 7, 8. Then we can express it as 7 of the i's, 7 of the x directions, and 8 of the y directions. So the vector 7, 8 will equal to 7i plus 8j. Well, this is very intuitive, and A is called the horizontal component because it's horizontal, and B is called the vertical component. All right.
Oh yeah, something that Eric didn't mention but is important is just make sure to like label your I because we know I is also means complex number. So put a hat on it or put an arrow, whatever, or boldface it. Now I'm just gonna talk about something else we can do with vectors, which is multiplying by a scalar, which is basically just some real number, like 1, pi, 4, they're all examples of possible scalars. So basically, in this diagram, this blue vector represents v, and this green vector, which starts at 0, 0, which isn't made clear, but it starts at 0, 0, is 2v. And we can find that out with this formula, which is really intuitive. It's just multiplying the vector by a scalar, and we just multiply it into the top and multiply it into the bottom. Intuitively, this is the exact same for our case, 2, 3. It's the exact same as the standard definition of multiplication that you learned in elementary school. And something important to keep in mind is when we multiply by a scalar, the directions are always the exact same. So that's a good way to check if you've made a mistake or something.
So here we have some basic properties of vectors, operations. Most of these are pretty easy to prove. So first we have vector addition is commutative. So the sum of so when you take the sum of two vectors, it doesn't matter what order you do it in. This basically comes from regular addition being commutative. So let's let V be A, B, and W be C, D. And this is A plus C, B plus D by definition. And then if we reverse the order, it's still the exact same because addition is commutative and adding the components doesn't really change anything. Mm, okay. The proof of the second fact is pretty similar, because like we're just going to be adding the three components, and since normal addition is associative, this is associative too. 0 is the additive identity, again for similar reasons. 0 plus A is A, 0 plus B is B. Um, these are all also pretty easy. So 0 times A is 0 and 0 times B is 0. So this is the 0 vector. 1 times A is A and 1 times B is B. So this is the same vector. Negative 1 times A is negative A and negative 1 times B is negative B. So this is the negative of this vector. Associative of scalar multiplication also comes from associative of multiplication, because multiplying B by C and then by A is the same as multiplying AB by C. And the distributive, and for the distributive property, like it's still pretty similar. A plus B times C is AC plus BC. So the corresponding pieces will be the same, and similarly, A times B plus D will be AB plus AD. So again, the corresponding pieces are the same. All of these basically come from the corresponding facts in real numbers.
All right, so here's some exercises, some true and false questions. Well, oh, this is not true or false yet. All right, first we have this question, which is about graphing vectors. Well, you don't need to actually graph the vectors. But like, let the blue one be U, so this one's U, and you label it. This one's U, and this one's V. I'll just go over part A because that's easy. So part vector u, the blue vector is 3 units right and 1 unit up. So u is equal to 3, 1. And vector v is 2 units to the left and 3 units up. So vector v is negative 2, 3. All right, you can look at the other ones. Oh, for part D, remember that, well, if you have the initial point, you can sort of like add the vector to get the final point, terminal point. Well, you don't need to graph them, just like maybe write it in coordinate form. Actually, as an example, I'll probably go over the sum of b. So let's go over half of u plus b. Half of u plus v. So this is half of 3, 1 plus negative 2, 3, which is 3 over 2, 1 over 2 plus negative 2, 3, which is negative half and 7 over 2, or maybe like decimals. So if you want to graph this, you sort of just go like half of u right here and v, which should end here. So if you draw these, okay, I can't draw, but like if you're like an artist, this in total, this would be half of u plus v. Or you can send the answers in chat for maybe C and D. All right, I think I'll pull someone random to do part C. Person 8. Okay. Okay, Helen, what's the vector W for part C?
Is it like -5/2? Wait, 5/-2?
Yeah, it's not really over, it's just 5, -2. But yeah, that's correct. Good job. All right, pull someone random for the other part. Okay, Elaine, what's the answer for part D?
I don't know.
All right. Well, I'll go over it then. Maybe I can pick another. Never mind. I'll go over it. So I said the initial point plus the vector is sort of like the terminal point. So the vector x, which is 4u plus 7v. 4u is 4 times 3, 1. And 7v is 7 of -2, 3. And according to the properties we've discussed, this is just 12, 4. And it's -14, 21. So if you add all of these, this is -2, so it'll be 25. So a vector x is -2, 25. So if we sort of add them together, like 8, comma -18, and then we move it by -2, 25, the end will be 8 minus 2, 25 minus 18. And this is 6, 7. So your answer is 6, 7. All right, we'll probably do a break after the next question.
All right, so there's a bunch of statements here, and basically we want to see if these are true or false. Uh, just to clear up everything, all the vectors start at the origin, and the endpoints are 3, comma 3, 7, -3, -4, -3, -6, 0, -13, 0, and -4, 6. All right, I can start going over these. The first one, the only real computation is finding a minus c, which is the right-hand side would be 3, 3 minus 4, 6, which is equal to 7 minus 3. And this is actually equal to b, so this first one is correct. What? Okay. The second one we'll look at d plus a and e minus 2f. And this one is minus 1, 0. And the other one, e minus 2f. Yeah, so we can see that these vectors are actually congruent, I mean identical, whatever, which actually means that they're definitely equal length since they're basically the same vector. So B is also true. And now A plus B plus C plus D. And I don't think this one's particularly challenging. We just add all the horizontal ones and the vertical ones. And this is equal to 2 and 3, which is definitely not equal to 0. So this is not correct. And the last one, E plus A plus D. Which is simply equal to 0 and minus 14. And if we look at f over 2 would just be half of this vector, which is equal to minus 3, 0. And these are definitely not the same, so part D is also wrong. I don't think these are particularly challenging since we're just adding numbers and subtracting like algebra 1. So I think you should be fine with these problems.
There's one additional thing I want to talk about. For like part A, like A minus C, you can have a particular interesting interpretation. Like for minus C, you can interpret this as A plus minus C. Minus C will be like the reverse of this vector. So it'll be like from here to here. So actually, A plus negative C or negative C plus A is just this vector. So this vector is A minus C. And you can see that this is indeed equal to B, as they're sort of translations of each other. Yeah, that's what I wanted to say. All right. So now let's actually have a break for about 5 minutes. All right, now it's end of the break. All right, is everyone back? All right, let's assume that everyone's back. Because I had this like timer thing. All right. Okay, let Jonathan talk about direction and magnitude now.
Yeah, okay. So at the beginning, we defined a vector as any quantity with direction and magnitude. So the magnitude of a vector is defined pretty similarly to the magnitude of a complex number. And it means the distance from the point to the origin, or like the length of the vector, basically. And it's usually denoted by double absolute value bars. So we can calculate the norm of a vector using the distance formula. So if this length is x and this length is y, then the norm is the square root of x squared plus y squared. So if we write that using the notation, we get this. A unit vector is a vector with a magnitude of 1, or a vector xy, where x squared plus y squared is 1. So as an example, we can find the norm of this vector on the left. So the horizontal component of this vector is 2, and the vertical component of this vector is 6. So the norm is the square root of 2 squared plus 6 squared, which is 2 root 10 or root 40.
All right, so here we have this new concept of dot products. So it's a new concept. So let's explain the new concept. So we have two vectors, like let's say this one's u, and this one, oh, that's already u. This is u and this is v. So we have u as u1, u2, and v as v1, v2. We just define u dot v. Well, it's already over here. Maybe if I write it with the actual vector. Okay, also a very important thing is that you must draw this dot in the middle. You cannot abbreviate this. You cannot just abbreviate it as this. This is incorrect. It's very important to note this out. And it's also important to say it's the dot product, because there's a different product that we won't cover in this course. It's called cross product, but it's like that's not important to pre-calculus for now. So like this is, you cannot write as this because there's two types of products and it's ambiguous of what type of product you're saying. So this is just a formula, and you just memorize this formula over here. All right, maybe I give you like 30 seconds to memorize this formula. It's pretty straightforward. It's like you multiply the corresponding components like this, and you like add them together. All right. So I'll just say over here, let's say this is v, and I'll just calculate u dot v. U is 2, 6. V is right 3 up 2. So according to the formula, this is 2 times 3 plus 6 times 2. This is 6 plus 12. So this is 18. So now we know that u dot v is 18. All right, any questions? Okay.
All right, so dot product has a lot of some properties, I mean. And let's just go through these one by one. So u dot v is v dot u. I think this one's pretty clear. Yeah, and we know the first one's pretty clear since we know multiplication is and addition are commutative. The second one, I think it's also pretty straightforward because we can basically just expand everything and we'll find out what we need to find out. But in this case, I'll show it anyways. This distributive property is also pretty straightforward. It's just a lot of computation. In this last part, we basically just group these two terms and these two terms together. In this last property, we basically just let u equals u1. And we know this is just the definition of the norm squared. This last one's probably the one that you'll see the most, since the first three are pretty simple to derive anyways.
Okay, so here we have some simple problems with the dot product. Okay, so for the first problem, we just need to use the definition. Also, this is a different way to write a 2D vector. This just means, oh, I'm using the wrong. This is a different way to write a 2D vector. This just means 1, 4, dot 3, 4, which is 1 times 3 plus 4 times 4, which is 19. Pretty easy. Okay, so for the second one, first we're going to plug in A and B into this expression. So we get 1, 4 plus x 1, 2, which is equal to 1 plus x, 4 plus 2x. So we need this equals 13, or by the distance formula, 1 plus x squared plus 4 plus 2x squared is equal to 13 squared. Yeah, okay, you'll find that one solution, if you solve it, then you'll find that one solution is 4, and the other solution is 17/20, I think. I don't really remember. Uh, 3 is pretty similar. We just plug them into this formula and solve another quadratic. I don't think it's very necessary. 4 is an example of the norm property. So A dot A equals 67.67, which is equal to 6 times 6 plus 7 times 7 equals 85. And by definition, the norm of A is the square root of 6 times 6 plus 7 times 7, which is the square root of 85. So this is an example of the norm property. Norm squared equals the product dot the vector itself. So yeah, pretty simple. Okay, problem 5 is true or false for any three vectors A, B, and C. A dot B dot C is A dot B dot C. So this is false because the dot product returns a number, and you can't take the dot product of a number with a vector. You have to take the dot product of two vectors. So this computation actually is impossible, so it's obviously false. For problem 6, this is also pretty similar to 2 and 3. A dot A dot B is equal to B1 plus B2, and the norm of B is the square root of B1 squared plus B2 squared. So that gives us B1 plus B2 equals 7, and B1 squared plus B2 squared equals 25. So it's pretty easy to see that the two possible values are 3, 4, and 4, 3 by the 3, 4, 5 triangle.
Okay, this part you can like, oops. Over here you can like explicitly calculate it, like make sure for yourself by doing b2 is 7 minus b1 and doing a quadratic over here. And b1 is 3 over 4. Or over here, actually you can indeed multiply a number by a vector, but it's just not the dot product anymore. So this thing is actually like a number times a vector. Like it's not dot product, it's normal product. So this is in the direction of C. And this one's in the direction of A because this one's a number. And you don't need A to be in the direction of C. Like A could be like 0, 1 and C is 1, 0. So this is like false in general, even though both sides are indeed defined. Okay, so one clarification over there. Okay, so we have very similar as in your complex classes, like a sort of angle, or yeah, the angle of a vector. So we have a vector and we like rotate it by some random angle. We have that, well, counterclockwise, and that angle will be called the angle of the vector. It's probably conventional to say that theta is between 0 and 360 degrees, or perhaps in radians, 2 pi. Then let's say the norm of the vector is a, well, this is a over here. So the length of this thing is a. So if we have this as theta over here, we can draw this right triangle. And then this horizontal distance will be a cosine theta, and this is a sine theta. So this vector, very similar to your complex numbers, this is a cosine theta and then a sine theta. And also very similar to your complex numbers, you can calculate theta as in, like, say vector u is x, y, then theta is arctan, the arctangent of y over x, and perhaps if you have the wrong quadrants, we need to make sure that this is plus 0 or pi. If u is in the third or fourth quadrants, you need to do indeed plus pi, as arctangent only returns negative pi over 2 or pi over 2. Actually, if it's in the fourth quadrant, it means you add 2 pi. Yeah, if it's second or third quadrant, you add pi. Anyway, just add a multiple of pi such that the quadrant is correct. And theta's in this angle range. Well, maybe I just talked about that. Okay, you make sure it could be 2 pi as well. or 2 pi plus arctan y over x.
Okay. This is a problem that I guess we'll work through. I want to give everyone some time to think. But first there's some notation that we have to, I don't know, notation, whatever it's called. This north 60 degree east thing, and this thing. Basically, north 60 degrees east means we start going north, which in this case will, it's conventional that's the positive y-axis. And then we turn 60 degrees east, which is conventionally the positive x-axis. So this north 60 degrees east is just a direction that indicates that this is a 60-degree angle. And this south 45 degrees east thing, it means we start the south, which is by convention negative y, and we go 40 degrees east, which east, as we know, is this way. So this is 45 degrees. So this is just what this means, like this notation. So now I'll give everyone some time to think about it. And if you have an answer, like feel free to message me.
You could use a calculator. Well, I think you must use a calculator.
Wait, I actually made a mistake here. If it says it's blowing from south 45 degrees east, it means it's blowing from this direction here. So the vector is actually pointing this way. That's on me. All right, I'll go through the first steps right now. The first thing we want to do is we want to make these actually vectors since it's like basically impossible to work with right now with just these. Actually, you could, but like that's not fun. So what we're going to do is we're going to draw a right triangle because that way we can easily see horizontal and vertical components. So this planes vector, I'll actually label it in red, is composed of a vertical vector. We notice this is just a right triangle. This is basic trigonometry. So it would be 300 upwards, and rightwards it would be 300 root 3. In the wind, which I'll label in blue, it would be 35 root 3 in both directions. So I'll just let the planes vector be P because it's convenient. So that means P is equal to, well, the wind is equal to, and notice that like when a plane flies, like it gets blown by the wind, right? Which means the wind is moving it. And we're just going to assume for simplicity, as these problems usually do, that like if the wind is blowing at like X miles per hour, the plane will move exactly X miles in that direction in 1 hour. Basically, in practical terms, what this means is that we can just add these vectors to find the final direction. And if we add these, let's just call it, I don't know, T for total. We get like some vector. Uh, and we need to find the magnitude and direction. We know a magnitude, we just square both components and add them, which we do with a calculator. Oh yeah, I made a mistake. Whatever. You get the idea. It's just 300 root 3. And if we square it, it would be, and take, if we like just use the Pythagorean theorem or norm formula, whatever you want to call it, it would be 585.798 miles per hour. And to find the final angle, uh, we would just take the inverse tangent of this thing, of the vertical over the horizontal, as we learned in a previous slide. And if we take that, we'll find that the angle, this is getting kind of messy, but let's say the plane's final vector is in orange here. Like we want to find this angle, like taking the square root, I mean the inverse tangent of the vertical over horizontal will give us that angle since it's in the first quadrant. So if we call this theta, then we'll find that theta is equal to 53.372 degrees. It's not? Oh, wait, hold on. Oh, yeah. In this case, it would actually be 36.628 degrees. Just calculation. And using this notation, it would be east 36.628 degrees north. Or you can use some other direction, north to east, whatever. But either way, you should get this same direction. You can notate it however you want, as long as the problem doesn't ask for something specific.
I have a question. In
Yeah, sure.
in the start, you said you made a mistake in the question. What was that?
Oh, the problem it said that like it said the wind was blowing from here, which means it's like blowing the opposite direction than this thing is actually pointing. Like if it's blowing from east, that means it's actually pointing west. Like normally, I think this is just like annoying. So, but yeah, sometimes they'll be evil.
Okay, thanks.
Is that all the questions?
So if you write it with north on top, the direction will be north 53.372 degrees east. Jonathan, are you here?
Oh yeah, sorry. Um, okay, so 10 newtons basically means that the gravity 10 newtons basically means that the gravity force acting down on it is 10 newtons. And we wanted the system to be balanced, which means that the three forces on this box are going to be adding to the zero vector. So we know that this is one tension force, and this is a so this is one tension force, and this is another tension force. The tension forces are in the same directions of the string. So like try to find the magnitude of the tension forces to balance out the system, I guess. Okay, so if you had a chance to think about it, so let's let this vector be the x vector, and this vector have a magnitude of y. So x is the magnitude of this one, and y is the magnitude of this one. So this vector is going to have a negative horizontal component since it's pointing left. And this angle is 46 degrees, so the magnitude of its horizontal component is x times cosine of 46 degrees. And similarly, the y component is positive and is x times sine of 46 degrees. Then we do something similar for y. The x component is positive since it's pointing right, and it's y times the cosine of 53 degrees.
We just
Um,
feel like the box is perfectly balanced.
yeah, yeah. And then this downwards vector is, well, it has no horizontal component, and its vertical component is minus 10. So this is 0.
So we have to solve that.
Yeah. Yeah, it's like, yeah, just use a calculator or something.
We need a bit more than a calculator, I think.
Yeah, you can write this as two linear equations and then like solve it like using canceling or something. Yeah, okay, if you had a chance to think about that, this is just a pretty simple linear equation in two variables. So we can just like cancel out to x using like just use a calculator because yeah, okay. Um we're going to find that x equals 7.033 and y equals 6.093 newtons. So yeah, this is how we can use magnitude and direction to vector components in physics problems.
I think in the textbook there might be some of these in the homework. Maybe I should explain the explicit way to calculate this set of equations over here. So maybe I write equation 1 as the one on the top and equation 2 as the one at the bottom. So if you look at equation 1, it implies that x cosine of 46 degrees is y cosine of 53 degrees. And this implies y is x cosine 46 over cosine 53. And after that, you can plug this thing inside of equation 2, and we get some linear equation x. So this will be x sine 46 plus y is this thingy over here. And, well, times sine 53 degrees. This minus 10 is equal to 0. You can like group the x terms together. I make a square. So you get x times, like the whatever this thing is. Oh, it's not over yet. This is 10. And you can throw that thing in your calculator. You get x is this number over here. And after that, you plug it into this equation 1 thingy, and you get y is whatever this thing is. So you get, yeah, that's how you do it with a calculator. All right, for those who are confused. All right, we have a little bit left. We have exactly one more question. This is also like sort of an application problem. We have two penguins standing, well, with the same mass. So Barry is this thing over here. Well, they were over here. Well, this moves here at 10, and they collide. And now Perry is moving like in this direction now. And now we want to find what's Barry's speed or velocity. So like this includes magnitude and direction. Alright, for this one, because the things are the same mass, they will probably tell you more, but I'll just tell you now that this vector 10 should equal to the sum of this vector of the Perry's 5 meter per second at 30 degrees north speed, and also the Barry's speed over here. They should equal to the sum. So say the initial Barry speed is, so let's say we set up coordinates like this. All right. So this initial one should equal to the sum. Use different colors. This one should equal to the sum. This one has magnitude 10. It should equal to the sum of the blue ones right here. So you want to find the blue one that we don't know. Oh, I already wrote that. I want to find the blue one that we don't know as 5 meters per second. All right, I'm gonna give you about, I don't know, 2 or 3 minutes. And I'll explain it in 2 or 3 minutes. Well, anyone with the answer can send their answer over. All right, I'll pick someone random to maybe give either the magnitude or direction. All right. Okay, Sarah, do you know either the magnitude or the direction of the velocity of Barry?
Wait, no, I unmuted myself accidentally. I don't want to talk. Sorry.
I'll just go over this. We have only like 3 minutes left or something. So the speed of Barry, if we look at this as a coordinate system where this is x and this is y, we have 10, 0 is equal to the speed of Barry. We can decompose as an x component and a y component. All right. All right, Sarah's saying that she got the answer. Okay, maybe you can send the answer while I'm doing it. We don't have much time left. So let's say this decomposes this 5 times cosine 60 degrees and 5 times sine 60 degrees. This is 5 over 2. And this is 5 root 3 over 2. And this plus some vector of Barry, which is vector b. All right, so this shows that vector b, if you like subtract it over, this is 15 over 2 and 5 root 3 over 2. And we like maybe use a calculator, probably don't use a calculator. And then we just find the magnitude of this. The magnitude of this thingy should be about 7.977 meter per second. And the direction is actually quite interesting. Direction is exactly 30 degrees over here. So the direction would be south 30 degrees east, if you use that notation. Wait, actually 60 degrees east, sorry. South 60 degrees east. We're at an angle of 330 degrees. Wait, maybe I messed up the calculation here. Let me make sure. Yeah, actually, I think the answer is 8.660 meter per second upon closer inspection. Yeah, there you go. That's your answer. Hey, good job. Yeah. Okay, so that's our session. Okay, thank you very much for coming. If you have any questions, remember we have office hours on Wednesday, and next session will be on Thursday at the same time. All right, thank you very much.